So we're back. We want to move on to this energy economy modeling, but I think that it makes sense, given that Jim didn't circulate the solutions to these homework sets, that I try to increase the speed a little bit and do them. That way, you guys may not be able to follow along, line by line, but at least then you have a complete set of values. And it seems there's a lot of learning going on. So let's see. I think we should keep going and see where we go. How well we do in half an hour or so.
Okay. So what are we on then?
I'm on to number 3. So
Number 3.
Number
All right.
2 is already done. So let's go to number 3.
Okay.
So this is going to be
This one's test.
it's a simple pure exchange model with 2 consumers with identical preferences.
Hold on 1 second.
A is endowed with X and B is endowed with Y. Just gonna fix this guy here. Endowed with Y.
Yes, okay, you're already sharing it, yes.
Identical preferences. Aggregate endowment of each good equal to sum of them, sum of Marshallian's demands. So exercise 1, set up the aggregate endowment of each equal to the sum.
The Marshallian demands.
So let's just pull these guys in. Like this, so that we have a little bit cleaner. Non-negative variables px1, px2, market x, market y.
So we need
Opening endowment of x. Okay, so here are variables starting value. So I'm going to say market x says endow. And I'm looking for the variable, it's called x endow. That's the good. That's greater than or equal to demand for x. So it says in exercise we can set up the endowment of each good equal to the sum of the consumer's Marshallian demands. So we're going to have the Marshallian demands. I don't know. Let's see. Oh, here we go. Oh, here we go. So now we can say equal to sum. So it's going to be x endow. So it's going to be, that's a multiplier. Because it's equal to 1 initially. It's going to be, so here going to be times 100. And then he says a Marshallian model. So consumers, the sum of the consumer's Marshallian demands.
something down of each good. Sum
I've
of the
written down
consumer-
the each.
sum identical.
Okay, so that's going to be Marshall. I guess I'm not sure what he means by Marshallian demand function. I guess it's going to be equal to 200 is equal to 200. That's the total endowment. It's 0.5 times 200. Consumer endowment. That's going to be PX1.
PX1.
This will be PX1 times 100 plus PX2 times 100 divided by PX1. So that's here I have a representative agent who says the sum of their endowments. So that's the total endowment. And then we have market Y. Says Y endow times 100. So that must be greater than or equal to, again, it's the same thing except it's divided by PX2. Set variables and solve. So it's going to be px1 dot L is equal to 1, px2, let's say model Marshall, market X, market Y, and px2 dot L is equal to 1, solve Marshall using MCP. And we have to get the variables. This guy goes with px1, and this goes to, this should be market. And then it's got, what's the X1 and X2? Oh, PY1, okay, I'm sorry. This should be PY1, Y1. So he has a different price. So he's gonna keep track.
It's not PA, yeah, I see.
It's PY1.
Yeah.
So this is model number 1. And this will be market Y dash PY1. I think we're gonna do another one. We have general for him. Okay, so that's gonna be Marshall using MCP, and let's just stop at that point and see. This guy should be exactly equal to, so it's as though we just add up the two consumers together. We don't have differences. Exercise dash Q3. Then we get a solution. Looks to me like everything looks okay. So PX1 is equal to 1, PY1 is equal to 1. So that looks all fine.
And we don't have to set lower bounds.
We probably should, it's like these guys get divided through, so maybe it's, yeah, probably a good idea. So let's put that bound. 1 even minus 5th. 1 even minus 5th. Avoid that function calls. A lower starting point. So that's this stuff. And then we go individual demands. So it's going to be, if I look at this guy, it's going to be parameter demands. D1. So that's going to be demands in model 1 by consumers on model 1. That's going to be D1 of X into A. So I'll just do this, all these guys. This will be Y. This is B. So I'm just doing this in matrix. And this is going to be equal to 100. That's the endowment is going to be 100 times cons 1. It's got 100 units of, what are they endowed with here? So A is endowed with 1, so 100 times PX1 dot L. And that's going to be divided by PX1. And then for 2, it's going to be like this. Y1, and then these guys go, and again, we have the same sort of idea here. This guy's endowed with Y. It's going to be by Y. So now I've got the demands, they're all going to be the same.
Okay.
At that point, right? Double the endowment of X. Okay, counterfactual. So this is going to be equal to and this will be benchmark. So let me just and I'd say it's called X endow. Two. And then we're going to say solve. And this is going to be the counterfactual. Let's take CF for counterfactual. And this is going to be, and the endowment of X. So this guy is endowed with X, that's agent 1. This is X endow. So this is the income of agent 1 is going to be PX1 times endow. In our model, we simply have a simple representative agent one consumer, whereas now we're evaluating what the individual consumer would demand at that point. The more complete way of doing it. So here we have variables are going to be WA, WB, PWA, TW, consumer income's got all these guys. Zero profit, market clearance, income balance.
Hmm.
Okay, so here we have to basically copy these guys and just get these guys. So I've just written down that's my list of equations I have to do. And now we have WA. Oh, and let's see, what variables do we have? This is PX. Okay, so this is the complete model. I'm just going to move these guys over. So we're going to have, this says that PX, the square root, I think they're both the same. The square root of PX times PY must be greater than equal to WA. Square root of PX, they have the same preferences. WB, the profit of X. Market for X says X in Dow times 100. It's got to be equal to, got to be greater than equal to I cons A divided by PX. It's going to be 0.5. Cons B. That's those guys, and we have the same thing for Y. That's those guys, and market for W. Oh, I'm sorry. Let's see. This guy was here. I just put in the demand function. So this is going to be equal to. I'm sorry. It's going to be 100 times. We have the W. That's the activity level. That's not. This is should be the prices or PWA. So I'm going to just change this. I'm going to do it without these. I'm going to make life easier by not putting those functions in. It just reduces the amount of headache we have to worry about. And we don't have this stuff. I'm just going to do it. Jim, I'm sorry, but I'm just going to do it this way. That's going to be mark. I don't need WA, and then that's cons I cons A is equal to, and that should be uppercase. Cons A should be like this. PX times X in Dow times 100. So that's all that stuff. Market clearance. Market clearance and then income balance. Market X dot PX. Market Y dot PY. Income. Wait a minute. Now I have two. I think this is named twice. Oh, it should be cons A and cons B. I'm sorry, my mistake. So this guy should not be I, but that should be simply cons A.
Mhm.
I just-
Okay.
So,
It's cons A dot cons A. Slash to finish off the declaration. Now we have to assign some values.
I think you also have a typo in your market Y, just so you can catch it now. Your first cons is cons S, cons BA, you see?
Yeah.
Okay, good. Yeah. Just so when you,
So here we have to get some variables assigned. turn it down here and say. One,
What happened if we forget this part, the lower bound, lower bound, yes, upper bound, what happens if we forget?
well, the thing
those?
is, if you're lucky, the solver doesn't run into the constraint. The question is whether or not
Corner,
whether it goes to a point that's outside the domain. You can't divide by zero, right? So, and if the solver is asked to divide by zero, it's going to complain. It's going to say, hey, wait a
Yeah.
minute, what's going on?
okay,
It doesn't know where the bounds are. So you should put them on. However, if you give it a starting point, which is close, it may be the algorithm is such that it doesn't actually go off to the boundary, in which case you're probably fine without the bounds. In this case, I think I would put it for. It's really just Py because the X is going to be fixed. This guy is going to be 1 e to the minus fifth. Now I'm going to go down here and I'll show you a trick here. This is going to be, I'm just going to copy the stuff. That's fine. Just, my approach is just to say, replace D1 with D2 and replace 1 dot with dot. Dx, and this should guy, okay, so I have the endowment. This is this guy. So do we have this right in the sense that there should be, no, that looks like that was wrong. Up here, it's 0.5 times that. And do I have this right? This says, okay, so that's the 2 of them, and that should be 0.5. So I have a mistake here in this guy. This should be equal to 0.5 times that. That's the budget share. He has 100 units and he buys 50 of one, 50 of the other. So it goes like that. And then these guys, I can copy these guys. This guy should be D. So D1 should become D2. And so that's going to be the solution in model 2. There's the command there. Solve, oh, and this is not going to be Marshall. It's going to be solve GE. Okay, so I have first one I solve with X now equal to 1. I save the demands, and down at the bottom I say, okay, option D1, 3 decimals, 2, 1, D2, 3 decimals, 2 rows, 1 column. Display D1, D2. That gives that guy. So let's see how that looks. So we have a bunch of solutions. Let's look and see what we get. There's D1 and D2. Something, I don't know what's going on.
they
Why
are
is
same.
X and Dow is not, there's no change in this case. Why is the X and Dow? Well, the counterfactual is going to be the same. Okay, so that's why is that the case? Oh, that's the demand there, but that's not the same as what you get in the model. Let's look what happened in the model. So in the model, the price just doubles. We have cons A and cons B in there. I don't understand what it's about.
This is what time it's like.
So let's just look at this guy.
I think we put the 0.5s.
Okay, there. We got, oh, so now we have a problem with things going to zero. Now we have to figure out, oh, we have to fix one of those prices. We have to normalize prices. So up here for the Marshallian model, we had a problem that didn't make sense. This guy is px1 dot fix equals 1. If I look at the prices bar px1,
FO is fixed. How do you fix the price? It's you fix the value of the price.
Yeah.
FX. FX. Dot FX. That is a suffix dot FX.
And LO is the lower bound.
Yeah. L was the upper bound.
so there's no difference. So it seems that there's no difference in the aggregate model. There's no difference because what's going on here is if the price doubles, and demand goes down by half, so the value expenditure doesn't change. The endowment is 200. Let's what happens to the demand here. So this says the demand should be. Oh, I know what the problem is. It's the PX1 and PX2. That's where the problem was. Okay, so I have to change, clear replace PX or X1 dot with dot. So I didn't have the right prices there. For the prices from the other model. So do B2. So there's demands in the first case for consumer one. The benchmark is 50-50. And the counterfactual, it goes to 100-100 because he has twice as much income. Let's see, demands by consumer one. This is the first one.
And the second one, B demand goes down to 50. Demand to B, right?
That's right. So counterfactual. B's demand goes down. No, B's demand remains at 50 because his income doesn't change. A's demand. So the question is, why is it that A's demand? Oh, because so agent A is the one endowed with X.
No, we're double that, aren't we?
But why does that? I don't understand there.
Yeah.
Let's say look at D2 here. So X. So that's the income of the first agent. Oh, and this is going to be Y and L, my fault. That remains equal to 1, so it doesn't matter. That's what. Oh, and here I have the wrong. This should be by PX. I see where the error is. That's PX. Should be PX1. X at the wrong. This guy should be Y and L to be precise. This guy should always be Uh, that's X down and Y and out, and it should be the same thing down here, X and out. Why don't I just have to do it here? Gradually getting there.
Yeah.
So in the single representative agent model, benchmark demands are 50. In the counterfactual, the price of X falls by a factor of 2, and demand for X goes up by 100%. In the second case, yeah, they both have the same effect. So here we have agent A's demand. So why is the agent B? Oh, because his demand goes up because I just don't understand why agent A in that case doesn't have more money. Oh, it's because exactly offset. So he doubles the amount of endowment,
Mhm.
the price falls by half.
By half, so you can see it.
So therefore his income goes down. So that means they remain the same. So there's no effect here other than the demand for X goes up by 50%. That's because it's called Douglas.
Yeah. That's a company. Okay. That's good.
That's just clearly a consequence of the Cobb Douglas framework. Yeah, if I were getting crazy, I could make a CES version of the same model. That's one. We'll do one more. These squares with
Oh, wait, you want, okay, 1 second. Let me open up a new.
the linear regression, y equals alpha plus beta times x.
You're gonna circulate all these, right?
Yeah.
Okay.
So I did a paper once in which the primal was politically incorrect and the dual was politically correct.
Oh, geez.
This was an assessment of a lawsuit that was brought against the University of Minnesota.
Oh, recently?
No, this was 30 years ago.
Because that was a recent one too. They messed up anyways, yeah.
So the women claim that they're underpaid at the University of Minnesota. And the judge says, how much should we pay them? How much should their wage go up? So we did a linear regression
Mhm.
and accounting for like 95 characteristics of every person. Where did you go to grade school? Where you,
Yeah.
you know, what you have, how much
Kitchen
experience you
sink
have.
of controls, yeah.
And then they end up discovering that women were underpaid at the threshold of, there was a threshold of like 5% that said has to be above this. So they basically said, in the regression, how much do we have to raise everyone to? And so the politically incorrect thing was, let's find the least amount of money we have to spend
Mhm.
through strategic raises to women on the payroll, such that the T statistic falls below the 5% threshold.
Oh, I see, to make it, yeah.
Evil.
So, exactly. I said the primal is politically incorrect. You're deliberately introducing noise into the regression, and you want to find where do you put the noise in to make it the most effective. And so what we do is we simply take the linear regression model, the optimization model and solve here.
Mhm.
We write down the first order conditions for that one, and then we optimize on top of that with an equation for what the T statistic is. So you have to write down the first order conditions that characterize what the equilibrium is, and you want to optimize through the addition of additional raises doing that.
Mhm.
The dual is politically correct. The dual problem is you have a certain amount of money to give out. What's the best you can do in terms of reducing? If you use that statistic as a measure of inequality,
Mhm.
what's the best way you can allocate the money to minimize to a fixed amount? So
That's
so it's the same thing. It's a
Yeah.
this problem. You take the dual and write it down. For years, I was batting off invitations to do legal lawsuits with this technique. I never cashed in on it. It was more that at the time, it was more just for me, it was like amusing that you had this problem that basically the complementary formulation gave you a new way of looking at the problem. I thought it was so cool. Okay, so now all I'm doing here is just lining that stuff up. There's the benchmark. I don't know what that is.
So variables, uppercase, parameters, lowercase.
Yeah,
That's the, okay.
so this has got the variables J1 and J2. I don't know why Jim likes this. I think I'd rather have that be observations. Let's use some names to know what we're talking about.
Oh, I see what you mean, yeah.
And then what's this guy? I forget what are the fitted values up here? He had this be alpha and beta, right?
Mhm.
So the alpha and beta. So why not? Why do you use J1 and J2? That seems like that's not. You can call it J, but that's going to be alpha and beta. So I'm just changing the notation just so it's easier for me to remember what I'm doing.
Could you go up a little bit? So is should it be, in one we have star, in the other one we have now comma,
The star
and-
says fill in between 1 and 6.
6, okay,
It reads the sub that there's a 1 at the end, and then it observes the same string with a 6, and then it says, okay, I'm going to put it on.
okay, okay,
And the cool thing is you can use A star Z.
Oh, to go from
So you
A
can
to
use
Z.
letters as well.
Yeah.
oh, okay,
So it's
okay.
just a way of generating a bunch of labels.
got it.
So that gives us this stuff, and now down below this guy, display data. And now there's the X. Oh, this is going to be Y, and this should be X. So this should be Y and X. Y and X. That's the data. I always forget what's what.
Oh, I see what you're saying, yeah.
There's the data, there are the observations, and now we have the variables.
Hmm.
I don't know why he's displaying this twice, and it looks a little bit crazy. Okay, so it tells us the stuff. Then we're going to variables will be alpha, beta, and sum of squared differences.
Mhm.
This will be the sum, uppercase sum over the square of, it's going to be, so now we have y hat, that'd be y minus alpha plus beta times x. It's going to be the square of y of I plus beta times x of I. Okay. That's the ordinary. Let these guys be the one. Let's just see if we go this far. So alpha is minus 0.42 and beta is 1.47.
Why did I give up that?
It's my hard drive someplace. Oh, have I got this guy? Oh, okay.
Go back to your code just for a sec. I just want to see some. Where did you, okay, 1 second.
share paper with you.
Scroll up just a little. To where you changed some of that other stuff.
I just changed some names because it drives me nuts. Using numeric indices, that's the reason I use modeling languages, so I can use the labels to know what stuff is.
Yeah, but we can't leave the old stuff though, right? It's got to be changed. If you
Well,
change the set, you have to change.
Yeah.
That's the issue. Right?
Yeah.
Okay.
So it's going to be E. Just looking for a paper. I want to give you a paper.
Yeah.
Optimization. One. Actions. So this was a lecture. This is some notes on using GAMS to solve these squares problems. Let me just see if I got this guy. Squares. Matrix 1. Seven. What I did with this paper. That's not one thing. Anyway, I won't worry about it. So if I go back here where we were, so that gives the whole thing, and there's this guy, and then finally we have first order condition for alpha. So if I look at my first order condition for alpha, it says that so alpha sum over I of y sub I minus alpha plus beta times x sub I squared. So the sum over I of 2 times this guy zero. So this is going to be, this guy will be equal to sum over I of y of I minus alpha plus beta times x of I is equal to 0. That's the first derivative. And then this guy is going to be minus the sum, it's going to be minus the sum over I of y of I. Oh, this guy doesn't either. So it's going to be x of I times y of I minus alpha plus beta times x of I. That's got to be equal to 0. So that gives me the first order. That's the OLS for the MCP. Alpha, beta, say, that was lowercase. So If I go back to my. As soon as we're done with this one, I should.
Now there's actually a question.
There is.
Semi-colon inline above. But I don't know when was.
Yeah, I
this
think
done.
some point here. That's. So now let's look at the solution we have here. So that equals solved. I do a back search for bar. And there we see you get the same solution, right? So those are known as the normal equations. That's just basically we solve the normal equations, the system equations. Then with respect to parameters. Do a plot. Let's not worry about that. Just do that like this. Okay, so I'm not going to do anything from the plot right now. We could do a plot of the output. Let's not worry about it. Output data. Now let's just look at number 5 just to see what it is. Sector specific capital. M3 allowed for sector specific capital. Recode this model to allow capital to move between sectors.
Well, we can try this one overnight,
Yeah. I
and then
was
you
just
can go
going
over it
to-
tomorrow. How about?
Okay.
Yeah.
What I can do is I can get these guys, I can write up the solutions to them,
Mm-hmm.
and that way we can start with that.
Yeah, that works. So it gives us some stuff to just kind of chew on. And now we have some already worked out ones, and you'll circulate those answers so we can, right?
Yeah. Yeah, I can do that right now. I can say,
Or that you have already.
yeah.
You can put them in Skype, Tom, it's fine.
So it's gonna be here. Solutions. I'm just gonna, well, I'm just thinking about it. Carefully, I'll just say from here.
Put the file, the zip file in the chat. And Colin, I'll send it to you.
Okay, perfect.
Okay, I'll do that. But there's, you can go to several things. I'd say, yeah, I won't bother us now. The thing is that people who wanted to come at, you can come at GAMS. I'll just say that there's a, if you come at GAMS from a econometric standpoint, you can write down econometric models very easily in GAMS. It's actually quite, and there's certain
I
econometricians.
see.
It doesn't automatically generate the, standard errors and so forth. So you have to do more of your own, you have to write your own equations, but there is a whole. So, there's a number of different approaches. So, and Irving Kavalagan on his page has a bunch more, but there's a bunch of different ones. So least squares is what we did right now. And you can basically go through, set it up as an NLP solver. This is easy to do. And that shows you how to get the statistics back. You can also do least absolute deviation, which is kind of a cool thing you can do with GAMS. So you can basically use an L1 norm rather than L2 norm for the minimum, that puts latest weighted outliers. So that uses this variable splitting technique. So there's a whole bunch of stuff you can do. We have a bunch of examples here of how to do this. So I need to find the paper that goes with this. I just have the lecture notes, so I'll find the paper that we have. So let's go back now.
To CS functions.
The CS functions, I'm going to go through an example now of a model. So let's build a little model in GAMS. So if we think about energy economy models and we're thinking about what was in the fable of the elephant and the rabbit, let's do a fable of the elephant and rabbit from scratch in GAMS. And so this is really not anything different than what Marx has been doing all this, except now we're going to have this elasticity that governs supply. So we have in some sense, we have a functional form with Y, with energy, labor, and capital. And then we have E, with which combines PR specific factor with output of the Y sector to produce energy. I'll come back to how that works.
Mm-hmm.
And then we have the represented agent. Oh, I have a mistake here. This is just representative agent. He sells labor. He consumes some of his own labor. He buys energy. He buys output. So there's labor leisure choice in the model. And it's also, you can see that in the adding up. So here we have 80 units of labor of time. He has 35 units of capital, and he has 5 units of the energy specific resource. So that's there. So if I go back now, I will look for my paper on CES. So this is I think it's called CS.pdf. Lecture notes. So this, I just downloaded this from the website. Funny paper. The first version of this I put up in like 1995, and then because we had a paper which I thought was spectacular. We had this spectacular paper that we had a hell of a time publishing, because econometricians see CS functions at that time. CS functions were considered something that's very lowbrow. Why would you do this? But we have this paper where we prove this property that CS functions are locally flexible and globally regular. In other words, you give me a point in the price space where you calibrate it. You give me the matrix of own and cross price elasticities at that point. You can come up with the CES nested function that will match that. That was kind of a cool result, because previously this flexibility thing was something that was only available with flexible functional forms, general as non-TF, translog, there's a variety of different functional forms. But those functional forms are all flexible, but none of them are globally regular. So they lose monotonicity, or they lose convexity. And so the CS function we have is nice. So this is a paper on those things, and I'm going to draw on a couple of things here from this paper. And the reason I'm going through this is not because I just want to dwell on details. Instead, I want to just point out there's something very important here, which is how to calibrate in an energy model. You need to be able to calibrate to a supply response. so this section 6 in this paper is quite relevant. So if you have benchmarking supply function, so if you have a function which has one factor which is specific and the other factor which is variable, then there's going to be the elasticity of substitution is going to be related to the elasticity of supply. So this means that in most energy economy models, you want to calibrate to say, make an assumption about what is the price of coal and how responsive is coal to the price, to the carbon price. You need to think about how to calibrate that. And in a CGE model, the easiest way to do that is to put in a specific factor that's only used for producing coal, and then control the elasticity of substitution between that specific factor and the variable factor that goes into produce coal. So you have two inputs, the production function. I go through the mathematics of this is laid out here. And essentially what it comes down to is if you have freedom to choose the elasticity, here's the key relationship, that the elasticity of supply is equal to the elasticity of substitution times 1 minus theta over theta, where theta is the elasticity, is the value share of the specific factor. So what this tells us is that if the value share of the specific factor is equal to 1/2, and the variable factor is equal to 1/2, then the elasticity of supply is the elasticity of substitution. That's the same. So I do that in the model that I put up here. I rely on that property. So I'm going to say here that I'm going to have a specific factor PR, which is the energy resource, and then I bring in a variable factor to produce energy. So energy gets produced by putting together the resource and the other thing. That's a very energy intensive economy. This one with the GDP share of this is around 5%, overall. And so, basically, this is the way. Oh, let's see, what did I do here? This is the wrong file. Maybe it's right one. I don't think I put investment. I don't have investment in this model. I don't know what I was doing. So this in a more complicated model for investment. This has no investment. So here I compute then the value share, and that's going to be, so if I look at, so once again, if we go up above and look at our model, and let me just see, use the board for a second. All right. So down. Yeah.
Can you turn on?
We need to change.
He just needs to stop sharing, right?
Yeah, stop
Yes,
there and not
sharing, but you need to turn on Tom, you need to change your video input from your laptop
Okay, I'll do that. in a
to the
second.
room.
I don't want this guy anymore. I want this one. I want this one. Now I'm going to say new share. I'm going to say video.
Stop sharing. Stop sharing. The right one, yes.
And then over here, I'm going to say video.
Mhm.
And I choose AverCam Pro 2, right?
Are you in already? Let me see.
I think I got it.
Yes.
Yeah.
Okay. Yeah, that's fine.
We can't hear you now. You're on mute.
Okay, can you hear us now?
Yes, thank you.
So I'm just going to get this stuff. It's going to be. So I'm going to produce. So this is an energy economy model, and the whole point here is just to remind ourselves of where we are. Is when Colin came, he said, "I'm happy to do environment, but I have never done this before." So I thought, let's walk before we run, and let's write down. So I'm trying to do the minimal model that's sort of a modern version of what the elephant rabbit model is.
Okay.
So this is an energy economy model. And the basic, so the Marshallian intuition here This is gonna be E bar. This is gonna be energy. That's E. This is gonna be PE. And we want to put a tax on between supply and demand,
Mhm.
and thereby reduce any demand that E hat.
Mhm.
E has the target. And the thing is, the magnitude of the tax then is this width, this distance here.
Yeah.
And the key intuition here is that the magnitude of the tax depends on the elasticity, so that if the demand curve is more elastic, then it
Yeah,
goes like
depends
this, right?
The shape of them, right? Yeah.
The slope's the shape of this curve, and the same thing goes supply and demand. So there's this interaction of supply and demand that determines how big the tax is. The black one, we have a tax that's this way. Here we have a tax that's just this is the tax if we have the more elastic one. Right? So
Yeah,
that's
that
the-
makes perfect sense.
the
Yeah.
perfect idea. So the thing is, if we're going to talk about climate policy or environmental whatever, we have to think about controlling those curves, right? Like what happens to the supply. Now, of course, in a more elaborate model, you might think about there being a step function. If we do a bottom-up sort of model, then we might have steps. There's a certain amount of wind available, and then there's a certain amount more of this stuff, so you can have steps. A bottom-up model, but a top-down model, we just want to control the elasticity. So I'm going to build the simplest model that can do this. And in the process, I'm going to do a little bit, introduce you a little bit of modeling stuff that we need to do this, right? So this will be, so this is going to be Y. Let me just see how I did it. I got to make sure I follow what I did. So I'm going to follow the merge style Y. That's going to be E. And that's K L. So this is a model that's just a value added. There's no intermediate inputs.
Mhm.
So we're going to have sigma E, which is the elasticity of substitution between energy and other inputs. Right. And then I think I just made that guy be, yeah, and I made this guy be one. So Cobb Douglas,
Mhm.
capital energy. Right. Yep. So then these guys each has an elasticity. Remember that we have an elasticity matrix sigma, which is going to be sigma. The off diagonal elements are sigma E L, or sigma KLE is going to be sigma KL, sigma KE, and sigma LE. Those are the three. All the other ones are tied down by the shares of the benchmark. So we have three free parameters, and when we specify a nesting structure, we're implicitly defining what these guys are. And we've defined it. This specification is such that these guys are just roughly equal to half, and they're the same. So we could think about how to do a different cross elasticity. There's empirically, it's not completely. Usually the empirical estimates suggest that capital energy are more complements than substitutes. So there's other things you could do, but basically this is a simple way to do it. And then on the consumption side, I'm going to assume that the consumption side C, I'm going to assume that we have, and again, we're putting labor here, and this is going to be goods. I call the good Y, that's the output of this guy, and then it's going to be E. So here I'm going to have this guy be sigma E. That's the same, and I'm assuming, and then I have this guy be equal to 1. So I'm just doing a different model here. So in the consumption basket, energies are imperfect substitute for other goods. And if I try to reduce energy, it's going to be costly, and I control how easy it is to reduce. That's the slope of the demand curve is by the single parameter of sigma E on both sides. So that handles the demand curve, how the demand curve goes. And now we want to think about the supply curve. What happens to the price? How easy it is it if we apply tax, what happens to the supply response? And that's going to be represented by a production function for energy, where we have a resource R and this macro good Y being combined. And we'll call that eta E. So that's going to be the elasticity of substitution between those two inputs which with a little bit of math, you can show is exactly equal to the elasticity of supply of the output.
Could you please repeat that? Elasticity of,
So the elasticity of substitution between, I'm going to bar over that to indicate that R is a specific factor. So R is only used in that place in the economy. So we have a specific factor. So if I have a specific factor for producing coal, then essentially, if the price of coal goes down, I may want to economize on my input of other stuff by not producing as much coal. I want to shift away from, I want to cut off some of the people working there. And the amount by which I reduce my output depends on how easily I can substitute away from other inputs to my resource. That elasticity of substitution determines how much my supply will
Okay.
respond.
yes.
If the other inputs are used in fixed proportion, that is to produce anything, I have to have 10 guys there. I'm not going to reduce the number of guys. I'm just going to take it on the chin. It basically says that the value of my resource, this guy, everything will happen here and the output will be unresponsive. So if this guy goes to 0, then the
Yeah,
supply
nice.
remains fixed
Mhm.
to a point where if you can't even cover the labor cost at all, the variable cost, then you're going to shut down. But basically, if this guy's 0, then you have 0 responsiveness. If this guy is highly elastic, then as soon as the price goes, I can substitute away from it. So that's the whole idea here, is that in a general equilibrium setting, you don't usually think about supply curves to a response function. Instead, think about it as being a specific factor and you're going to respond to what the prices are. At least this is one way of doing it. And that's the way I've done it in this model. So now I have, if I go back to my Marshani model, now I have a model where I can control both the slope of the demand curve and the slope of the supply curve.
Mhm.
Right? And so that's going to be important for what the cost is of reaching a given target, or how much of a tax we have to reach this given objective.
Yeah.
Is going to depend then
Yeah.
on what those things are.
Elasticities are, yeah.
Right. And this is sort of in the world of a smooth system of equations, this is the way you normally do it.
Mhm.
I'd say, let me just take a break let me just jump over for 5 minutes just to the other way of doing it, which is not. So if I go to, I'll gotta remember to do this here, it's called pi's MCP. Oh, no, this is not the one I wanted to do. It's a different one. It's called Marshall. Like Samuelson.
Can you share your screen again, please?
Yeah. Okay, so let me just go through the beginning. I'm just going to make one quick comment about relating this to the Marshalling model. There were 2 questions in the chat, or
No, that's resolved.
okay. I'm just going to break for 1 second just to go off, just to say what I'm doing here is one way of going at this, and there's another way of going at it is to describe what the technologies are. I'm just going to say, and I'll put these lecture notes up on the screen. So this is just to help orient you to the way we think about these things. And Samuelson was just essential for this stuff. This is again, both he and Samuelson and Mann were both amazing. They both enrolled in 16. They both were out. And it's amazing. And they both did the same thing. It's like Samuelson was like, again, another guy, as his emphasis plays an incredible role, but he went to MIT, proceeded to hire like.
Yeah,
The
like,
thing about this guy's brilliance about who he chose, he hired like 5 guys with Nobel Prizes. It's like, he's an unbelievably clever guy. Like, one theory that all the social sciences are both true and non-trivial, the theory of comparative advantage, right? So this is So I just wanted to go to this one little example. I'm not going to go off to I have an electricity dispatch model. I have spatial price equilibrium. There's more stuff in these lecture notes, and you can look at them. I won't spend the time, but I just wanted to say, to compare this, what I'm doing here on the energy supply, to this other approach. So bear in mind that what we're doing here with the energy supply is we're using a local characterization of supply responsiveness, which is like locally sort of in the neighborhood of the benchmark. How much will output change if the price goes up or goes down, right? So it's describing locally what the curve is. The other approach in this game is to talk about technologies, where you say, this is a technology which doesn't exist, but I know it's sitting there on the shelf.
Mm,
And so even though I have the equilibrium, local equilibrium is characterized, there's an equilibrium, another equilibrium out there. And that's, if you think about it, that's really this activity analysis world. You could have an activity analysis world where you have multiple dimensions. So here I have a price and a quantity, but if you add in a third dimension, which would be the carbon coefficient, then there could be something that has a very high price and has no carbon. So therefore, you could be picking things that could become cost effective. This is the way engineers think about climate policy, is about what the costs are and what it takes to get there. Whereas economists tend to think locally. There's clearly a need to think about both dimensions, right? So there's like
so
what's,
basically, if you drive the price up so much, it would bring in some technology that doesn't use carbon. Is that
Yeah,
right?
so the thing
to
is,
make it
or-
actually cost effective.
yeah, it's just saying that I think it's important to bear in mind that the framework we use for the analysis is really conditional on what the simulations are you want to run. Right? So if the idea we're talking about net zero, to do a local elasticity and then do net zero is kind of crazy, right? And that's the challenge now with climate, is that all these policies involve huge reductions, and with even any sort of the elasticities are low, you're not going to get there. It's like really, you need a really high price to get there. So that's the basic point here, is that this sort of equilibrium approach. Yeah, so that's just, I just want to make this point. And I usually, when I am trying to motivate, it's a little bit of a tricky game, because we're trying to motivate the complementarity approach is really the ace in the hole we have, is that we can handle boundaries. But then lots of the models we solve are from the literature that don't have boundaries. And the model I'm putting together now does not have a boundary. This is just, and so let's go back to the model and just see how it works. Oh, I was going to do one other thing before I go back. Let me go one more time here. So this is just the structure we're going to use. And now I'm going to just say, this guy, I'm going to write down. And this is just getting back to the thing yesterday. You said, okay, well, where did we have these macros that describe uncompensated demand functions. Wait a minute, where did those come from? And okay, and you said, oh, but you just knew the answer. Yes, I knew that.
Yeah, oh yeah. That's right.
Okay, so the thing is, here, I can just write down that if I'm calibrating to a Harburger equilibrium where all the prices are equal to 1, I can write down the cost function on inspection. Okay? The cost function is going to be C sub y. It's going to be equal to theta E times PE to 1 minus sigma E plus 1 minus theta times PK to the theta K, PL 1 minus theta K, all to 1 minus sigma E, all to 1 over 1 minus.
I see. That's a CES function.
That's a CS function.
Yeah.
We're relying on this calibrated share representation.
Mhm.
Which in the calibrated share representation is one that says this, I calculate the value shares at the reference point, and then that gives me a unit function. It's something that we'll evaluate to 1.
Yeah.
And the structure of the unit function is the CS, the cost of a CS unit function is going to be equal to the sum over I of theta I times P sub I to 1 minus sigma, all to 1 over 1 minus sigma. And the way to think about this, when this guy is equal to 1, then we're summing across the thetas, that goes to 1, this guy disappears, and I have a 1.
Yeah.
And this characterizes the supply response. Now, there's some mathematics I'm asserting that. I'm not proving it, but I'm just saying. And then if we have a nested function, I put the nested price index on the inside. And this guy's called Douglas. That's 1, then this gives me that guy. And here I have to say theta E is equal to E bar, if prices are all equal to 1, divided by E bar plus K bar plus L bar. And theta K is going to be equal to K bar divided by K bar plus L bar. Right? So that's the way we simplify stuff. We make this And it's tedious sometimes and it can be ugly. And that's the reason I'm a big fan of finding a macro that encapsulates all the ugliness and then you don't have to look at it. Then the cost function is just sum up the demand functions and all sum together, but this is where the whole thing begins with this calibrated sort of form. And I have so the lecture notes on the CS functions. There's it goes down some rabbit holes or some stuff that's not directly related, but price elasticity of supply, how to calibrate, all the stuff is directly on target for what you want to be familiar with.
That's the 2002 document.